All right, welcome to our additional structural modeling literature review design meeting. I'm going to basically cover some of the ideas and fundamental concepts that we'll use in creating a systematic or structured literature review associated with structural modeling. The initial area that we're going to focus on are the publications and the information that was published in the years from 1950 to 1975. And we're going to look at work that was done by John N. Warfield, Donald V. Stewart, and Andrew P. Sage. There may be others, and we'll explore that as we go forward to see if there should be others that are should be on this list. There's some very interesting aspects of the modeling approach and the mathematics and the concepts that were being used from 1950 to 1975 that strongly impact the structural modeling practice, concepts, and application. So what we'll do is we'll basically have a bit of a review here of what's going on, because we have a number of things that are happening, and an approach that I think that will work is to actually talk with, review the backgrounds of these three individuals that we've listed here. And so we'll start with looking at a publication review, papers and monographs that were published by John N. Warfield, and I will bring that up now. Okay. So stop sharing, there we go, then we will start sharing. We'll share this one. Okay, and so what we see here is we're looking at the papers and monographs for John N. Warfield. This is on the GMU site. So we'll go down here to papers and monographs, and this section looks at papers and monographs from 1953 to 1965. The interesting aspect here is the focus on not only mathematics, but also on the electrical engineering and the application of mathematics to electrical engineering applications. So we see that 53, we have a table of steady state transforms. Also, the synthesis of dynamically variable electronic filter. An interesting one here is a United States Department of Commerce publication on systems engineering. And then the optimum diagnostic sequence for systems with one faulty element, or how do you detect faults. And then how to improve systems engineering. A note on the reduction of switching functions. And as it goes on, basically it looks at analog computers and how analog computers and circuit theory can be applied to logic and logical systems. This is very interesting from my point of view, because the work is a little bit, is not really well known today. Most of this type of analog work is for computer circuits, has gone to digital integrated chips. And so this is not well-known information anymore. And then as we look at 65 to 73, we can see that there's a a lot of publications on transistor mixers and switching circuits and the synthesis of switching circuits, which is important, and we'll discuss why that's important as we go forward. And then the switching networks is model of a discrete stochastic process. But then we start in the late 60s, we start seeing information like what is systems planning, or larger scale type of applications of some of these activities to large scale social systems, the delta chart and method for R&D project portrayal, and public system planning now in unified program planning. We're looking at large scale applications of these basically circuit design and mathematical techniques. And then 73 to 75, there's a large number of publications here on intent structures, which are a type of structural modeling approach. And binary matrices and systems modeling. This is a very important paper on matrix mathematics and matrix application, especially the ideas of circuit switching and how you analyze the structure of a matrix. And it's it assumes that you have some background, I think, in switching theory to understand what it says, and of course developing subsystem matrices and so forth. So what we have here is we have a Moorfield was trained as a mathematician, then did his graduate work in communications and electrical engineering, and wrote a number of publications on the application of the mathematics and the ideas of switching theory to different types of problems. So I'll just mention that some of Moorfield's early books, let's see, let's pull those up here, are associated with computer design. And here we go. So let me bring up these first two. Share these. Share these again. I'm going to go over here. We're going to find this particular one right here. Bring it up. Okay, this is 1959, which is Introduction to Electronic Analog Computers, which focuses on the mathematics applied to analog computer design. It's not digital, it's analog circuits. It's dual circuit switching theory. There's a lot of interesting things in this particular book. 1959. Then in 1963, 4 years later, he wrote a Principles of Logic Design. And this goes into binary logic and how you create logic circuits within analog and digital computers. So it treats some circuit theory and circuit switch matrices, and it also treats type of digital logic. So fundamentally, the background where Moorfield is coming from is background in mathematics and analog computer design and digital computer design, focused on the logic design of these systems, which is provides the foundation to be able to understand the rest of his work. Then we'll look at the people that we had, other people we had listed there, which was Stewart and Sage. So let's take a look at Sage's publication list. So we will switch over to that now. And bring that up. Let's find it here, which would be right here. Okay. Now we can see this starts from 2010 until today, so we'll go to the earlier works. let's see, okay, so we have 1967, operator algebra for differential systems, which is a type of circuit and mathematical approach. And we have nonlinear sequential algorithms for estimation of uncertainty, combinatorial algorithms for discrete detection and likelihood ratios, and algorithms for discrete sequential maximum likelihood. Now, these are all types of electrical engineering and mathematical algorithms that we're publishing here now in the 67, 71, 72, 73. Then we start here with an introduction survey of group decision making. Now that's out of electrical engineering, starts to get into large-scale social systems, which is interesting because that's about the same time Warfield was publishing his work at Battelle. In fact, Sage did some of the review of the work that Warfield did at Battelle. We'll go into economic cycles, which is now getting way away from electrical engineering and into the control of systems and large-scale social systems. So interesting types of work, but basically Sage's background was in electrical engineering and communications, and mostly focusing on continuous types of systems that were represented as matrices. Not a lot of information here on binary matrices, Boolean matrices, switching theory, things like that. You don't see that in Sage's early work or in any of his work, really. So then we'll go and look at Stewart's work. And they found, well, let's see. So let's go ahead and bring up the next one here. We'll find Donald Stewart, wherever he is. Okay. I know I have it here somewhere. Here we go. So I found it. Now I just need to find it here. Here we are. Bring this up. And this is the list of Donald Stewart's papers on ResearchGate. Go back to 1959. This article here on the algebraic foundations for constructing optimum algorithms. So Stewart was interested in optimizing computer time, hardware time, resources in solving systems of equations. So he's looking at constructing optimum algorithms to solve these equations. Of course, that's still a very important area where algorithm design and algorithm efficiency is extremely important today. 1962, on an approach technique for the analysis of structure of large systems of equations. And then 65, partitioning and tearing systems of equations. So here, what we have now is Stewart is focusing on the solution of systems of equations. So not switching theory, not switching matrices, but basically all systems of equations, which is interesting because it's a subset of the type of work that Warfield did, and it doesn't address a very important part of the switching theory that also uses matrices and certain types of matrix mathematics that came out of analog computer design. So with Stewart's work, we'll see again that his early work was focused on systems of equations. And then in the 80s and 90s, that kind of translated over to application to larger scale social technical systems. And we will, again, continue to take a look at that and see how that background impacts his work. So in this particular case, let's go back and look at our overview here again, so we can just kind of get an idea of what's going on. And we will look here with the screen share. We've got this, and we'll screen share it again. Here we go. I think this is it. Bring it back up. Yes, okay. So we've done a kind of a quick run through here. 1950 to about 1975 on Warfield, we saw that essentially Warfield started with with degrees in mathematics and degrees in electrical engineering and communication theory. We worked in analog logic and digital logic on the mathematics side, and also in designing the filters, and designing the physical components. So we had a complete fundamental background in this area. Stewart's work was focused on and publications were focused on the optimal solution of large sets of equations. The circuit theory, the analog logic, and the digital logic don't appear in Stewart's early work. And that is, again, so Stewart only covered kind of a subset of what Warfield did. He had a subset of the background. And then Sage's work also looks at a very interesting area, but again, he has a background in electrical engineering, and the circuits and the circuit theory part seems to be applied, and is mostly to continuous systems, not digital systems. So that was kind of the takeaway for looking at this overview of the work here. And this becomes important when we start addressing one of the fundamental questions that Kevin had about the algorithms, the structural modeling algorithms, and that is, well, how do we address the matrices? And how do we use the matrices? So this overview of the background was intended to provide context within which we could start talking now a little bit about the matrix applications and the matrix approaches. So I'm going to now go and look just briefly at the systems of linear equations approach here, which is right here. We'll share this. This is in Wikipedia. And so all three of the authors that we're talking about deal with systems of linear equations, which are essentially from mathematics, and they have a set of equations which have dependent and independent variables, and solution processes that include eigenvectors, simplex method, a number of other ways of solving these types of equations. But they're fairly straightforward, they're very well known. And what we have is an application, a well-defined space in mathematics that deals with the solution or the representation of a linear equation. So nonlinear equations usually are also linearized to kind of approximate a solution. But what happens is that these equations have dependent and independent variables. In mathematics, when you're solving equations, fundamentally, you have these two types of groups of variables. In switching theory, you may be able to represent some of your problems with mathematics that have these components, but in switching theory, it's basically the concepts of dependent and independent variables are either not used at all, or basically used in different ways. So essentially, we have a matrix approach where we're just looking at our matrix applications for structural modeling. We really should start making a separation between the Boolean switching theory matrices and the types of activities that you do with linear equations. So I think this is a very important distinction. And of course, other thing that Kevin brought up was the idea of how eigenvectors impact the solution. So eigenvectors are going to be used in the solution of systems of equations that have dependent and independent variables. There's a number of techniques that are well defined where you can determine that. You have your dependent and independent variables here. So what we have, of course, is that we get to the idea of setting all of the variables on the right-hand side to 0. You go through and look at those. And then you can do some applications that help you solve for the variables on the left-hand side in the matrix. That's really an important technique, but it doesn't really translate directly to the ideas that are used in switching theory or a switching matrix. So a switching matrix is a square matrix that essentially represents the switches in a physical system, and a simple switching matrix can be constructed from resistors, transformers, capacitors that are connected. And so that essentially we're looking here at a representation of analog circuits. And this is the background that Warfield had. Switching matrices, diodes, cores, resistors. So the switching algebra and switching matrices are are different than working with a series of equations. And we can look here at network theory. Switching matrices associated with combinatorial circuits. Fundamentally, a component that Warfield has throughout his work, his early work, and all his work, is that it's a Boolean matrix. The switching can be represented, so because it's Boolean, either 0 or 1, then the switch can be represented as a switching matrix. And the mathematics that go with the switching matrix are very important. So these are some of the just fundamental points and observations that we've come across in working to understand the differences in the solution approaches that were prepared and were presented by people. So we will go ahead and, well, actually by these 3 specific people. We'll go now and bring this back up again. Yeah, we'll share this one. Okay. So fundamentally, what I would say is that what we found is that the Warfield's work integrated switching theory and matrix and equation theory almost interchangeably. And this I think, created a few problems. And it was created a few problems for people who we're not familiar with the overall work, and it also created problems for solution types of processes. But I think some of the problems started with people that were looking at the Warfield's early work. Some of his early work in structuring complex systems is important. But the foundational piece, I think it's really interesting, is his Battelle monograph, and Battelle monograph #1, June of 1972, a unified systems engineering concept. And these ideas of terms and concepts that are used in this particular Battelle monograph are outlined in the glossaries. And one of the more important things, more interesting things, is there's actually 2 glossaries. There's a glossary that is Appendix A, I believe. Right. So Appendix A is just a word glossary which has just general words all the way through, and it has 2 definitions for a matrix. And this matrix definitions then have become important. The first definition in glossary A, just general word glossary, is a mathematical entity formally defined in mathematical text. So he recognizes the formal mathematical matrix. But then the second definition is a 2-dimensional array, in which some of the entries along one dimension have some interaction with the elements along a second dimension. The nature of the interactions being indicated by entries in the intersections of the dimensional entries. So this then is a matrix, like a switching matrix, where the switch is on or off, right? But the second type of 2-dimensional array for a matrix, that definition fits. And that's in the general word glossary. And then in this book also, he has Appendix B, which is the mathematics glossary. And he goes through and there he defines matrix in a mathematical form. So definitely 2 different views and concepts and ways of handling a matrix. One that has to do with switching theory, or a relationship between a set of entities. And the second one, of course, is the standard mathematical definition. So fundamentally, in structural modeling, we go through to a literature review. I think that has to be one of the things that is highlighted early on, is what type of matrix, what type of mathematics, and separate out the switching theory from the regular mathematical solutions. And in many cases, this apparently has been quite jumbled up in the published literature. And what we should do for a structured review is to actually use this as a high-level filter. So when we're looking at a paper, we should really make a distinction of whether they're using regular systems of equation mathematics, or they're using switching theory mathematics for matrices, using a combination of both. And is the problem that they're addressing, is that problem actually a switching relation type theory? And are they using switching relation type mathematics? Because it's been my experience when I've looked at these, is that in many cases they've applied, they are attempted to apply the solution, the mathematics that you use to solve systems of equations. They have tried to apply to systems, structural problems, which really should be represented using switching theory or just a Boolean matrix. And after 1975, or around 1975, actually 72 to about 80, Warfield further defined the mathematics of the Boolean switching theory as it would apply to almost any general relationship. And then what we've done after that, Mary and I have done after that, is we've looked at the logical properties associated with each of these types of relationships that are used in a switching matrix type of problem, and detailed, exactly what those are, what those logical property groups are, and how they would impact a relational matrix or a switching matrix. So as we use these approaches and thread through them, they become very important. And I think it's foundational then for the literature review. So Mary, does that make sense so far?
It does. It's a fairly comprehensive statement of what we hope to accomplish, at least at the front end of things.
All right. What I would like to do also then is, as we go back and we think about in the years from 1950 to 1975, where most of the people we looked at here started in clearly a technical mathematical analysis area. Then they moved to a more social technical application of their techniques to more social technical system design, organizational design, product design type of applications. And we'd like to also, in the literature review, come up with candidate characteristics and attributes that would allow us to categorize and evaluate the application of these methods in each case and make a determination of whether or not it seems reasonable. So we could have a kind of a sliding scale of, well, this seems like a reasonable approach. It's the type of solving a system of linear equations, and this is a problem that's represented as a system of linear equations. So that seems like a proper application of the method. In other cases, we've seen where the problem was not represented as a system of linear equations, but as an aggregated combination of events or sequences or series or some type of well, it looked like you just had a little hiccup in the video conference here. We lost conference. I think we're live now, though. Mary, if you want,
Yes, it's coming.
Scott.
Yes, I can hear you now, and we're still live.
Okay, Matt. I have a little hiccup during the podcast. I'll see if I can bring these back up. Let's see. What would you like to review now? Okay, so these what's that book? Those books. All right. So I will and bring this in back up. First, okay. Again, what we want to look at here is the idea and make a distinction, come up with some characteristics where we can actually look at and what's being what has been publicly discussed and to make a distinction whether or not we should be using circuit theory type of relational approach or
The
using
sound is picking up pretty badly.
okay. Well, we have problems with this particular class. I think what I will